All right, welcome to Note 6.1. In these notes today, there are two main concepts that we are going to cover. And the concepts deal with square roots and other kinds of roots. So we all know what a square root is. A square root is something like this, where I'm looking for two of the same numbers that multiply together to give me 9. And we know that if we were to type that into our calculator, we would find out that the square root of 9 is 3. But what we would find out also is that if I typed into my calculator 9 caret and then open parentheses 1 divided by 2, so 1/2, then I would also get 3. And that's because we can take any kind of root and we can write it as a fractional exponent. Okay, so a square root would be written as a 1/2 exponent. A cube root, which is what I have going on here, and I know that because there's a little 3, right? When there's nothing, it's got an understood, let's see, an understood 2 right here. We understand that that means square root. Well, when we actually write it out, that means that it has a different root. It has a cube root. And so another way I could write this would be negative 27 to the 1/3 power. And the thing I like about writing the roots as fractional exponents is because it makes a little more sense to me. So for example, when we would do the square root of 9, we would say that it is the square root of 3 times the square root of 3, and then we would bring a 3 outside the radical. Okay, well that's just kind of a process that we understand. But if I tell you that I have 9 to the 1/2 power, right, that's 3 times 3 to the 1/2 power, it's basically saying take half of these things and that's your answer. So my answer is 3. Well, same thing here. I know that I'm looking for 3 of the same thing. In this case, the 3 things that make up negative 27 are negative 3 times negative 3, which gets me positive 9, times negative 3, which gets me a negative 27. So I'm looking for 1/3 of those things to be my answer. Well, there's 3 of them, so 1/3 would be a negative 3, and that is my answer. So another thing I want you to notice is that when we have a negative under the radical, if the number outside is negative, if the number outside is odd, then it's perfectly okay. We're going to get an answer. It's going to have a negative 3. Right? Remember when we would try to do the square root of negative 9, we wound up with an imaginary number as part of our answer, right? We'd get an I. That does not happen when we have an odd root. When we have an odd root, your answer is just going to be negative. There's no I involved. All right, so this is basically the same thing as 1 to the 1/6 power. Either way, whether I take the 6th root of 1 or raise 1 to the 1/6 power, my answer is always going to be 1. Because 1 times 1 times 1 times 1 times 1 times 1, I don't know, was that 6? Is 1. All right, so here we've got 625 to the 4th root, and that can also be written as 625 to the 1/4 power. And remember, what we're doing is we're looking for 4 of the same number to get our answer. And we know if it ends in a 5, then it's divisible by 5. So I get 5 and 125, and I get 5 and 25, and I get 5, and I get 5. So I've got 1, 2, 3, 4 5s, and I'm going to take 1/4 of them, which would be just 1, and that would be my answer. So my answer is 5. All right, let's try it with negative 32. So odd, which means our answer is going to be negative. All right, my answer is going to be negative. So I can basically just deal with the 32, and then I just know that I make it negative at the end. So 32 divided by 2, I've got 2 and 16. I've got 2 and 8. I've got 2 and 4. I've got 2 and 2. 1, 2, 3, 4, 5. I've got 5 2s. So I know that I want to, we can also write it like this, 1/5 of them, or just one of them, is going to be my answer, and I'm going to make it negative because my number under the radical was negative. So my answer is negative 2. How are we doing? All right, so now we're going to move on to these things called rational exponents. And all it is we've taken a number and we are at the same time raising it to a power and taking the root of it. So we've got a number, I'm going to call that n, and I'm raising it to a power and I'm taking the square root of it. So power over root. Power over root. I want you to remember that when you see these fractional exponents. Okay, so for example, this 125, it's the third root of it, and it's raised to the second power. So you can either write it like this, 125 to the second power, and it is the cube root of that, or you can take the cube root of 125, so cube root, and you can raise all of that to the second power, whichever one's easier. Now, if we look at this, if we square 125, we're going to get a really big number, and then we're going to have to try to factor tree it to find the cube root of it, so that's going to be a little painful. However, if I've memorized my perfect cubes, I know that the cube root of 125 is 5, which means that when I take the cube root of it, I get 5, and then I just square that 5, and I wind up with 25. All right, so here I have the cube root of 8, right, because it's power over root, raised to the negative 4 power. Well, we know that the cube root of 8, because we've memorized our cubes, is 2. So it's 2 to the negative 4 power, and then we know we never, ever, ever leave our power as a negative, so this becomes 1 over 2 to the 4th power, and then 2 times 2 times 2 times 2 is 16. So my final answer, hopefully, is 1 over 16. All right, so what does this one mean? Well, 9 to the negative 1 over 2. It is the square root of 9 to the negative 1 power. Square root of 9 is 3. 3 to the negative 1 becomes 1/3. And that's all there is to it. It's not so bad. Okay, so these next ones they want us to do in our calculator, and there's a couple of different ways you can do it. I want you to take out your calculator, and I want you to do this along with me. So you can, for this first one, let's do it like this. Let's type in 24, and then we're going to use the caret button, and we're going to open parentheses, and we're going to raise it to the 1/4 power. If you don't have parentheses, you're going to take 22, you're going to raise it to the first power, and then you're going to divide whatever you get, which in this case would be 22, by 4. So you will get a wrong answer. So let's do this one now. So I'm going to take 22, and I'm going to raise it, open parentheses, 1 divided by 4, so to the 1/4 power, and that gets me 2.1. This is the nearest thousandth, that's 3 decimal places. So we're talking about 2.166. Okay. If we had done it incorrectly, I'm going to do it incorrectly for you really fast. So 22 caret 1 divided by 4. You can see we get 5.5, which is very much the wrong answer. All right. So over here to B, we are going to take 35, and we are going to raise it, open parentheses, 5 divided by 6 power, and we get 19.352. Remember, all right, and then this guy, so we could type into our calculator 11 to the 4th power divided by 5, right, 5th root, power over root, or let's show the other way we can type into our calculator. So we can, since we want the 5th root, you push the 5th button, and then you come down here to second, where is it, math, and nope, not second math, just math, sorry, and we come down here to number 5. All right, so this tells me I'm taking the 5th root, and then it was of 11. All right, 5th root of 11, and then I'm going to raise that to the 4th power, and that gets me 6.089. And if I had taken 11 and I had raised it to the, open parentheses, 4 divided by 5, close parentheses, I also get the same answer. So we know we did it right. All right, so my answer would be 6.809. So 6.809, and that's how easy it is to in the calculator, which is why we don't ask you to do it that often. But we will ask you to do it sometimes, so be sure that you know how to do it. So the reason why we're even talking about all these funky roots is because we want to be able to use that concept to solve equations. And remember how back when we were doing quadratic functions, which was, oh, say, like last week, if we could get it to be something like x squared equals a number, then we could just take the square root of both sides. All right, same thing applies here. If we could get it to be power equals number, then we can just take whatever root that power is to both sides, and we can get our answer. So your very first step is to isolate the power. So in this case, we've got our power multiplied times 6. So we're going to divide both sides of our equation by 6. So we get x cubed equals 64. And then we are going to take the cube root of both sides, because a cube root undoes a cube. So that leaves me with just x. And over here, it leaves me with 4, because I have memorized my perfect cubes, and I know that the cube root of 64 is just 4. Do I have to put the plus or minus? Let you think about that for a second. Okay. The answer is no. No plus or minus if, this is a big if, root is odd, because we just learned that back, let's say right here, that if we had an odd root, then the power, the sign, whether it's positive or negative, was the same thing as the sign under the root. So up here, since we have a positive under our radical, then our answer is going to be positive. It's only if I have an even root, like a 4 or a 6 or an 8, then I would need to put the plus or minus, because then both the positive and the negative roots apply. All right, so what am I going to do to this one? Well, I am going to take the 5th root of both sides. Now, over here, that gives me an x minus 8. I really didn't need those parentheses, but since I wrote them, I'm just going to leave them. All right, so then I need to figure out if 100 contains 5 of anything. Well, we know that 100 is 10 times 10, and we know that 10 is 5 times 2, and 5 times 2. So I do not see 5 of anything, which means that this has to stay the 5th root of 100. So my final answer, when I add 8 to both sides, is going to be 8 plus the 5th root of 100. It was not a plus or a minus because the root is odd. So going back to this guy over here, if the root is odd, we don't use plus or minus. Okay, we are just going to add in this case. All right, now we are going to move on to 6.2. So just a couple of days ago, we learned about our properties of exponents, right? Which were if we were multiplying two things that had an exponent, we can add. If we were dividing, we subtract, and so on and so forth. Well, those things still apply to these rational exponents. And rational just means that my exponent is a fraction. Okay, so we know that if we have, for example, here in A, 2 bases, same base, right? Each raised to a power. Then when we multiply, we add powers. So this will become 12 to the 1/8 plus 5/6. Now, we remember from all our work with fractions throughout our lives that when we want to add fractions, we have to get a common denominator. In this case, the common denominator, both 8 and 6, the smallest thing that they divide into evenly is 24. So I'm just going to deal with the exponents right now. To get 8 to equal 24, I have to multiply by 3. So I have to multiply top and bottom of that one by 3. And then to get 6 to equal 24, I have to multiply top and bottom by 4. So what I'm really going to have is 3 over 24 plus 20 over 24, which means that I get 23 over 24. So it will be 12 to the 23rd over 24th power. And that is my answer. That can actually be reduced, but that is way too complicated for a video. So remind me and I will tell you about that tomorrow. All right. And then what is the power of this 10 right here? If you said 1, then you were right. And we know that when we have two bases to the same base, each raised to a power, and we are dividing, that we subtract. So this would become 10 to the 1 minus 2/5. We know that 1 is actually 5/5 minus 2/5. Oops, that should be a 5. So I really wind up with 10. 5 minus 2 is 3. Keep the base. We'll keep the denominator. So it's 10 to the 3/5 power. In example C over here, when I am raising a power to a power, I multiply. So 4 times 1/5. This is really like 4 over 1, which means that I get 4 over 5, right? Multiply across top, multiply across the bottom. So I get x to the 4/5 power. And that's my answer. Not so bad. Okay, so order of operations still applies when we're doing things like this. So PEMDAS tells me that first I have to look inside the parentheses. Can I combine these? The answer is no, they don't have the same base. This has a base of 5, this has a base of 7, so they can't be combined. So now I should go to exponents. Raising a power to a power, I multiply exponents. So 5 to the 1/3 times 3, and that would be times 7 to the 1/4 times 3. So over here, 1/3 times 3 is just 1, so that leaves me with 5. 1/4 times 3 is 3/4, so that leaves me with 3/4. Can I now multiply these two together? No, they're not like terms, so I have to leave it like this, or if you'd rather do it like this, either way. But I cannot multiply these two bases together because this one is raised to a power. All right, over here, raising power to a power, so I am multiplying. I get e to the 1/3 times -3 times f to the -2 times -3. So over here, this gives me e to the -1. And this gives me f to the +6. We don't leave negatives in our exponent, which means this guy has to go down to the bottom of our fraction. So this becomes f to the 6th over e, final answer. All right, looking at this, 2 to the 6 and 4 to the 6, those are not like terms because they don't have the same base, but I can write 4 in terms of 2. So I've got 2 to the 6. 4 is 2 squared. And then that is raised to the 6th power. And then it's all of that to the -1/6. All right, so here's where it starts to get fun. So raising a power to a power, I get 2 to the 6 times 2 to the 12th to the -1/6 power. I do inside my parentheses first. Each of these has a base raised to a power, so I add exponents. That gets me 2 to the 18th to the -1/6. 1 divided by 6. All right, multiply. So 18, wait, didn't really need those parentheses today. Come on, eraser. It's not cooperating. Okay, so times -1/6. Well, remember, this is 18 over 1. I'm just going slowly for those of you who don't enjoy fractions. All right, so I get 2 to the -18 over 6. Well, -18 divided by 6 is -3. So it's 2 to the -3rd power. But we never, ever, ever leave negatives as exponents. So this becomes 1 over 2 to the 3rd. And then because I have my cubes memorized, I know that 2 to the 3rd is 8. So my final answer is 1/8. Not so bad. You just have to go step by step by step. And I wrote out every single step. You obviously, once you get the hang of this, would not have to write that many steps. All right, in this next section, we are just taking things that we already know. Right? We already know the properties of square roots, and we're just extending it to all kinds of roots. So for example, we know that if I have the square root of two things, then I can split them apart until they're the separate square roots. Well, same thing holds true if I have cube roots or fourth roots or anything like that. Okay, my quotient property says the same thing. If I've got division going on, then I can split it apart into the root of each, the root of the top over the root of the bottom. Okay, so same thing with square roots, just applied to other roots. So for example, here I have the third root of 12 and the third root of 18. Well, my property tells me that I can combine them together. This can be 12 times 18 because there is the same index over the radical. Now, I could multiply these two numbers together and try and get a really big number that I could then try to factor tree to look for a third root of. But I think it's much easier to actually factor these in place and look for 3 of the same thing. So we know that 12 is 4 times 3, which is 2 times 2 times 3. And then I know that 18 is 9 times 2, which is 3 times 3 times 2. So if you look at this, I have 1, 2, 3 2's, so I can bring a 2 out. I have 1, 2, 3 3's, so I can bring a 3 out. And remember, these are all factors, so I'm going to multiply. When I bring anything out, I'm going to multiply. And that means there's nothing left under the radical, so my final answer is 6. I can also, if it's easier, take the cube root of it. Well, we know that the cube root of 125 is 5, and we know the cube root of 8 is 2, so we know that our answer here is 10. So whatever order you want to do it, you can do it. Now here, I'm going to go ahead and do the division, right? Because it says if I have two things that each have the same index, then I can combine them. And I know that 80 divided by 5 is 16. So it's the fourth root of 16. And then I know, let's see if I can simplify it, that 16 is 4 times 4, which is 2 times 2 times 2 times 2. Well, there's my 4. I've got 4 2's, and it's to the fourth root, so I can just bring out a 2. Another way to think about this is if I have 4 2's, that's 2 to the fourth power, and then I've got the fourth root of it, so that is to the 1/4 power, and 4 times 1/4 is 1, and I wind up with 2 to the first power. So that's just another way of thinking about this whole process. All right, and here, again, I've got division going on, and they've got the same index, so I can go ahead and actually do the division. And this gets me the fifth root of 32. And then I don't think any of you are going to be shocked to realize that 32 is 2 to the fifth power, and these two undo each other. So again, my answer is 2. You're going to start to recognize all of these powers of 2 after a while, and they'll make your life a whole lot easier. Okay, just like we had when we had square roots, we have like radicals. And like radicals just mean they have the same index, so the same number and same radical and same number under the radical, then they are like radicals. And when we add or subtract like radicals, we just basically add the number outside and keep the radical. So for example, 7 to the fifth root of 12 minus basically a 1, right? There's an understood 1 out here in front, fifth root of 12. These two are exactly the same, right? Same index, same number under the radical, which means that they are like radicals. So I just take 7 and subtract 1, and I get 6. So I would wind up with 6, the fifth root of 12. Keep the radical, just deal with the coefficients. Here, this and this, even though they didn't look at it, this is really 9 to the second, right, cube root. That's what that means. So these are like radicals. They're exactly the same. So I add their coefficients, and I get 12, and I keep my radical, and I'm done. Now these two are not like, because they have different numbers underneath the radical, so I have to see if I can get them to be the same. Well, I know that 81 is 9 times 9, which is 3 times 3 times 3 times 3. Well, here's 3 3's, which means since I have a cube root, I can take a 3 outside the radical. And then I have this lone 3 right here left over. So I have 3 cube root 3 minus. All right, let's deal with 24. So 24 is 2 times 12, which is 2 times 6, which is 2 times 3. Well, here's my 3 2's, which means a 2 can come outside the radical, and this 1 3 is left over underneath it, which means I have the cube root of 3. Now I have same index, same number underneath the radical, which means I can go ahead and do the subtraction. 3 minus 2 is 1, so my final answer is 1 cube root of 3, or just cube root of 3. So the concept remains the same when we start dealing with variables underneath our radical. We're still looking for the same number of items underneath the radical in order to bring something out in front of the radical. And we know, furthermore, that we can still break them apart, right? So this becomes the cube root of 64 times the cube root of y to the 6th. And we know that the cube root of 64, because we've memorized our cubes, how many times have I said that now? A lot, probably. Some good advice, though. So cube root of 64 is 4. And then this one, I want you to think about it like this. We know that it is power over root, right? And furthermore, we know that 6/3 simplifies to 2. So I wind up with 4y squared. I think that's the easier way to go about doing this, rather than saying that this is 6y's and we need 2 groups of 3, so we wind up with this. All right, so this is 4th root of 625, and then times, and I'm just going to go ahead and write it straight away. So it's z power over root. The 4th root of 625, we've done it before, it's 5. And then you can factor tree it if you don't remember that. 12 divided by 4 is 3, so it's 5z to the 3rd power. All right, over here, we've got all of this raised to the 1/5 power. So we know that this is 32 to the 1/5 power, and we know that this is m power raised to a power, so it's multiplication, 5 times 1/5, and n to the 30 times 1/5. You should remember at this point, because we've done it several times during this set of notes, that 32 to the 1/5 power is 2. M to the 5th times 1/5, that's just m. And 30 times 1/5 is the same as 30 divided by 5, which is 6. Pretty straight. All right, so this looks spectacularly complicated, but it's not if you just break it apart. So it breaks apart into 56 divided by 7 times a to the 1st divided by a to the 5/6 times b to the 3/4, and there's no other b, so that's it, times, and then this c is on the bottom, and it's negative, so we're going to move it up top, so it's times c to the 3rd. All right, let's put it all back together. So 56 divided by 7 is 8. 1 minus 5/6 is 1/6, so a to the 1/6, b to the 3/4, c to the 3rd. And that's my answer. Not that hard. All right, let's split this apart. So we have the cube root of 6, which we can't do anything about. And then we have times x to the power over root, y to the power over root, z to the power over root. Okay, so this gets a little more interesting. So 3 goes into 4 one time, so we get an x outside the thing, and then we have a 1/3 left over, right? So this basically is x to the 3/3 times x to the 1/3, which means I'm going to have an x join my 6 here underneath the radical. 9 divided by 3 is nice and even, so we get y to the 3rd, so we have no y's left over. 3 goes into 14 4 times, so I basically have z to the 4th, and then there are 2 z's left over. So z to the 2/3. So because this still has a remainder and this still has a remainder after I bring out my z to the 4th, underneath my radical I have a 6 that comes from there, I have 1x that comes from there, and I have 2 z's that come from there. That was a little more complicated. So another way to think about it is to think about it like this. So underneath my big long cube root radical, I have 6, and I have 4 x's, 1, 2, 3, 4, and I have 9 y's, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I have, oh my god, 14 z's. Are you really going to make me do this? Z dot 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 z. All right, so this first set of 3, that's where I got this x from. And this x right here, so this set of 3 went to here, this x went to here. And then I have 1 set of 3, 2 sets of 3s, 3 sets of 3. So no more y's left. They all came to right here. And then I had, trust me on this, had I written out z 14 times, I would have 4 sets of z's that went here, and then I would have 2 z's left over that went here. So it does get a little more complicated, but this is my final answer. Okay, E over here should be pretty easy after the one we just did. Same variable under the radical, same index of the radical, which means that these are like radicals. So I just take 18, subtract 11, and I get 7, and then I keep the radical. So cube root of u. F here works pretty much the same way. I've got a to the 4th, a to the 4th, b to the 2/3, b to the 2/3. These are like radicals, which means I just add my coefficients. 15 plus 8 is 23, and I keep the a to the 4th, b to the 2/3 power. G over here, I do not have like radicals, right? I've got different numbers and variables underneath my radical, so I need to see if I can make them the same. I've got 7 s's, which means I can take 4 of them out to give me another s outside. So I've got that 10, I've got that s, and then that leaves me with the 4th root of 5, can't be simplified, and I took 4 of these s's away, which means I still have 3 left. Let's look at this one over here. 80, and let me see, is 8 and 10, and 8 is 2 and 4, and 2 and 2, and then 10 is 2 and 5. So here's my 1, 2, 3, 4. I've got 4 2's. So a 2 can come outside of the radical, keep the s, and then I have the 4th root. The 5 over here, it has to stay underneath it, and I've got s to the 3rd power. So now I have like radicals, and now I can just combine. 10s minus 2s is 8s. And then I have the 4th 5s to the 3rd power. Not so bad. All right, I realize this was a fairly long lesson, but we are done now, and you can go do your homework, and I promise you your homework will be no more complicated than, let's say, this problem right here, all right, which is the most complicated problem we probably faced today, and it wasn't all that bad, was it? And be sure, if you have any questions on these notes today, that you ask me in class tomorrow. Do your homework. Bye.